Swayam Prabha. Digital India. Educated India.
Let us start this lecture with a thought process that a positive attitude creates a positive thoughts, like chain reaction. We have already seen chain reaction, how it leads to explosion, and vice versa is also true. Hence, it is prudent to harness positive attitude to get success in life. If you look at in last few lectures, we are basically what you call derived the governing equation for mass conservation and species conservation, momentum conservations, and today what we will be doing, we will be looking at energy equation or energy conservation equation. So, in this energy conservation equation, what we will be doing, we will be basically looking at a very simplified form by neglecting the radiation heat transfer, heat transfer due to radiation, and also there will be dissipation due to the viscosity of the fluid, that we are not considering. Right. These are the things we will be neglecting. So, let us now look at energy transport equation or conservation equation. We will be deriving this, and of course, we will be considering basically also the heat generation due to chemical reaction, not due to nuclear reaction, right. So, let us consider basically a two-dimensional infinitesimally fluid element. So, this is 0 0, this is delta x 0, this is delta x delta y, and of course, this is 0 delta y, and this is your phase A, phase B, phase C, and phase D, and that is this is nothing but your what you call control volume, and it is infinitesimally small, that we have already done several for other governing equations. So, if you look at the, that is, we will have to do a balance of energy, right. So, I can write down rate of accumulation of heat in the control volume, right. And that is equal to the rate of heat entering into the control volume and rate of the heat entering out of the control volume, plus what it would be? It will be the heat being released due to chemical reactions, right. So, that is rate of heat entering into CV minus rate of heat out of CV plus the rate of heat release due to chemical reaction. And as I told earlier that we are not considering what you call heat release due to the nuclear reaction. However, you can consider there is nothing as such, you can derive the expression, but we are not considering because it is not concerned to us, right, rather that is a rival for the combustion process, or for so far the power generation is concerned. So, coming back to that, what is this what you call the rate of accumulation of heat? Accumulation of heat in this control volume, what it would be? That is basically dt rho Cp T, right, into volume. Volume is delta x into delta y into 1, right. 1 is basically perpendicular to this plane in which I have drawn the fluid control volume. And this, if you look at certain rate of heat entering into control volume at the phase A, right, along the x direction would be what? Would be rho Cp T, then there will be some heat transfer due to what? Due to temperature, already I have put, right. This is of course this, and then Vx should be there, this is a flow, right, and then what else? There will be some heat conduction, right, diffusion of the heat has to take place through conduction, right. So, I can say K dt by dx, right, and what will be going out? Will be going out, if you look at, this is at this point, and then this will be what you call, if I say this is at x, right, this will be then rho Cp T Vx, right, minus K dou T by dou x at what? X plus delta x, right. I can do that, means at this point, if I say x is 0 here, right, then it will be at delta x. Now, what will be the heat as a amount of heat entering into Cv through phase A, of course along x direction, what it would be? What will be rho Cp T Vx, right, this is basically flux, right, into K dt by dx, right, into the area, because this is a flux. So, this will be area element delta y into 1, this is at this phase, right, and amount of heat leaving Cv through phase B along x direction would be, it will be rho Cpt Vx, right, minus K dt by dx, I can write down into delta y into 1, right, plus dou by dou x into rho Cp T Vx minus K dou T by dou x into delta x into, I can write down basically delta y into 1, yes or no, that area through this area through the B. So, therefore, the net heat along x direction, what it would be? It would be minus dou by dou x into rho Cpt Vx minus k dt by dx delta x into delta y, right. One I am not writing. Yes or no? Okay. So, in the similar fashion, I can write down along the y direction, that is rho Cp T Vy minus k dt by dy, right. And similarly, I can write down rho Cp T Vy minus k dt by dy, y plus delta y. So, therefore, in the similar way, we can derive net heat transport along x direction would be dou by dou x dou y rho Cpt Vy minus k dt by dy into delta x into delta y, right. So, keep in mind that I can say this as equation 1 and this is my equation 2, this is equation 3, right. So, what will be the heat release, rate of heat release due to the chemical reaction? The rate of heat release due to chemical reaction would be basically what? Summation of m dot I triple dash I, right, h f I naught I is equal to 1 to n, right. It can be n number of species, whatever it is participating in the reactions, right, into delta x into delta y, into 1 should be there, that is the volume, okay, into 1 will be there. So, this is your equation 4, right. Now, using equations 2 to 4 in equation 1, we can have rho Cpt. Oh, I think I have forgotten another equation. Okay. It should be actually this is 2, this is 3, this will be 4, this will be 5, right. So, this will be 5. 2 to 5 in equation 1 we can have right, and you can divide this by the delta x into delta y across the equation, then you can get plus what you will get? You will get dx rho, I can write out this better, Cp T plus dou rho by dou y rho Vy Cp T, right. and is equal to by dou x k dou t by dou x plus by dou y k dt by dy plus m dot triple dash I h f I naught. So, keep in mind that this is basically equation 6, and this equation is having, this is your what you call unsteady terms, right. Term, and this is convective terms or heat convection, I can say, along x this is your heat convection along y direction, and this is of course heat conduction along x heat conduction along y direction, and this is your source term, heat release due to chemical reaction. And this term basically which is also known as a source term, the heat release due to chemical reaction, is highly non-linear in nature. Okay. Why? Because you will be knowing these things provided you know the species conservation equation, and not only that, we know if we will use Arrhenius form of that will be also dependent on temperature. So, this is a highly non-linear terms, and which will be also these equations are basically coupled, also has to be solved together. So, keep in mind that what we have here neglected is basically gravitational force, the energy due to gravitational force or electromagnetic or the any body forces we have not considered, radiation we have not considered, and the viscous dissipation, the energy loss due to the viscous dissipation we have not considered. Those are things, if you look at and consider that, then it will be quite complex. If you want to see that, you can look at the energy equation given in the principle of textbook, principle of combustion by Kenneth Coe, right, K. Coe. So, that you can see is quite complex. So, but however, we do not need, because those things are not relevant, and also particularly viscous dissipation is very very small as compared to the heat release. So, you do not need to consider that. And let us look at this, let us rewrite this energy equation for cylindrical coordinate system or for axisymmetric, for axisymmetric flow using cylindrical coordinate system. I will be considering RZ. We can have rho Cpt dt plus rho Vz Cp T plus 1 by R or rho Vr Cp T dz k dt by dz plus 1 by R dou R by k R dt by dr plus I is equal to 1 to n m dot triple dash I h f I naught. Keep in mind that this is basically Vr is the radial velocity component, Vr is velocity along radial direction, and we are assuming symmetric along the theta direction, right. So, therefore, we are not considering that. And these are equations like which are meant for 2-dimensional situations. However, you can also write down 3-dimensional as such, but we do not need in this course. So, therefore, we are not considering it. And let us now look at for the steady flow what will be this equation. I will summarize, and also how we can simplify it little bit further. So, we will do that. So, if you look at, let us now summarize, right. Let us look at all conservation equations, right. Equations for steady 2-dimensional flow, and we are using Cartesian and coordinate system only. We are considering now. If you look at continuity, that is the mass conservation is nothing but rho Vx by x plus rho Vy dy, right, is equal to 0. And let us consider x momentum equation for steady flow, that is rho Vx x plus rho Vx Vy y minus dp by dx plus x mu dvx by dx plus dx, this would be plus rho g, I am saying for gravitational forces, right. Now, if you look at, if I will take this portion, right, this portion and try to expand it, what I will get here, that I can write down as Vx dou rho Vx by dx plus rho Vx into dou Vx by dou x, right. I can write down similarly Vx Vy by dou y plus rho Vy by dvx. Now, if you look at these two terms, this one and this, if you will add, right, what will happen, right. I can write down as, let me write down Vx, like common, if I will take rho Vx by dx plus y plus rho dx dvx plus rho vy dvx by dou y. So, this will be 0. Why? Because of continuity equation. If I say this is equation 1, so right. So, therefore, by using this, if I say the equation 2 becomes, right, by I will use, that means only this term will be remaining, right, in this convection term, right. These are basically convection term in x moment. So, x momentum would be basically rho, what I can write down, rho Vx dVx plus rho Vy dVy right, y is, then rest of the things is similar, plus 1 by x mu dou Vx by dou x plus dou y into mu dVx by dy plus rho g. Similarly, I can write down, this is basically equation 3, I can write down as y momentum rho Vx y by dx plus rho Vy y minus dou p by dou y plus y by dou x plus dou Vy by dou y plus rho g y, this is g x, right. I mean gravity can be in one direction. So, any one of them has to be neglected, 0, right. If I am considering in this case g x is the vertical direction, the natural g x will be there and g y it will not be there, right, it will be 0. So, but I am retaining it just for the completeness sake, and the species equation I can write down similar way, y I by dx plus v y dy I by dy and by dx rho dij dy by dx plus by y rho dij y plus m dot I triple dash, right, and this is my 5, and energy equation would be in a similar fashion. I can write down Cpt by dx plus rho Vy Cpt dx is equal to xk dCpt by dx plus d by dy k Cpt by dy plus, I will write down plus here m dot I triple dash hf I naught I is equal to 1 to n. Keep in mind that this equation, x momentum, y momentum, species equation, all these equations are looks to be similar in nature. If you look at, these are your convection terms along x direction, this is what also these are all convection term, pressure drop of course is there, but there is a lot of similarities between these diffusion terms like viscosity and diffusivity and conductivity, and of course the source term are there in the species and energy equation, right. So, we will be making lot of simplification when we will be dealing with that. Generally, let us say if we are considering y direction, the diffusivity along the y direction is considered, whereas the diffusivity in the x direction will be small. So, it is neglected. We will be doing that thing later on. We will stop over here and we will see in the next lecture about how to deal with little bit boundary layer I will touch upon. Then we will see how we can eliminate the source term which is the culprit, because that is a non-linear term, that we will do. Thank you very much.